Welcome to the Explainer. Today, we're jumping right into the tiny world of semiconductors to solve a pretty big puzzle. It turns out the key to our technological future might just be a perfectly pure crystal.
So let's really dig into that question. What if perfect purity is the absolute key to our technological future? To get there, we first have to uncover this fundamental secret that, believe it or not, every single semiconductor holds.
All right, to really get why purity is such a big deal, we've got to talk about what makes a semiconductor, well, a semiconductor. It's this little secret hidden deep inside its atomic structure.
So picture this. Inside a semiconductor, you've got these electrons just kind of hanging out in their home base, right? It's called the valence band. But to do any real work, to carry electricity, they have to make this big leap up to a higher energy level, the conduction band. And that space between them, that's the forbidden gap. And this gap, this is where all the magic happens. It's the source of a semiconductor's power, its amazing ability to switch from being an insulator to a conductor.
Think of it like this. At absolute zero, when it's super cold and there's no energy, no electrons can make that jump. So it's an insulator. That's your off switch. But add a little energy, a bit of heat, some voltage, and boom, electrons start jumping across that gap. Now it's a conductor. That's your on switch. And that simple on-off ability, that is the foundation of every single transistor, every processor, every digital device you've ever touched.
Now, this whole on-off thing leads us to two main flavors of semiconductors. You've got the pure, all-natural version, and then you've got the one we've intentionally tweaked for better control. So first, let's talk about the intrinsic semiconductor. This is the pure stuff. Think of it as the raw material in its most perfect, untouched state, like a flawless crystal of silicon. In this state, everything is perfectly balanced. The number of electrons that manage to jump the gap is exactly equal to the number of empty spots or holes they leave behind.
But here's the thing. For most of the electronics we use every day, pure isn't what we want. We actually want extrinsic semiconductors. This is where we get our hands dirty and deliberately introduce impurities. The process is called doping. We basically sprinkle in a few atoms of another element to create an excess of either electrons or holes, and that gives us incredibly precise control over how it conducts electricity.
And this table here really lays out the trade-off perfectly. See, the intrinsic, pure stuff, it has pretty low conductivity. But by doping it, we make it extrinsic, and suddenly we get high controllable conductivity. That control is what lets us build all the complex gadgets we love. But what happens when you absolutely need to start with a perfectly pure material just to get your foot in the door?
And that question brings us right to our central mystery today. What happens when you have this incredibly promising new material, but it seems to just defy every attempt to make it in its pure intrinsic form? Well, this was the exact puzzle facing scientists working with a material called indium selenide.
Okay, so meet indium selenide, or INSE for short. This stuff is what's known as a van der Waals material. Basically, it's formed in these super thin layers that slide over each other easily, which makes it naturally flexible. On top of that, it has ridiculously fast electrons. I mean, we're talking about a dream candidate for the next generation of powerful, bendable electronics.
But there was a huge problem, a massive one. No matter who made it or where they made it, the properties of INSE labs were measuring were, well, they were all over the map. Key things like electrical conductivity were varying by more than 4 orders of magnitude. It was like everyone was following the same recipe for a cake, but one person got a pancake, another got a rock, and someone else got soup. It made no sense.
It turns out the issue was the standard recipe everyone was using. This quote gets right to the heart of it. Because of the material's really unique thermodynamics, the process everyone was using was just fundamentally unstable. It simply didn't work.
You can think of this phase diagram as a complex recipe book for growing crystals. And following that old recipe, it was guaranteed to fail. It resulted in this lumpy, uncontrolled mess that always had way too much indium. And that extra indium wasn't actually part of the crystal. It was acting like an unintentional impurity, a dopant that nobody wanted.
And this is what led to a giant misconception that sent researchers down the wrong path for years. Because all of these flawed samples were swimming in extra indium, which donates electrons, everyone just assumed that INSE was naturally an N-type semiconductor. But the big question was that its true nature, or is it just a symptom of a really, really bad recipe? To finally solve this puzzle, scientists basically had to throw out that old, busted cookbook and invent a completely new way to grow this crystal, one that actually respected the super tricky thermodynamics of INSE.
This was nothing less than a quest for the perfect, truly intrinsic crystal.
And the method they used was incredibly clever. It's called the traveling solvent floating zone technique. Now, instead of just cooling a big blob of melted material, they created this tiny, super hot molten zone with a very specific indium-rich composition. Then, they slowly fed a rod of the raw INSA material through it. As it passed through, a perfect single crystal started to grow out the other side, all while keeping that delicate chemical balance just right. It's really brilliant.
And wow, just look at this. This is the stunning result. For the very first time, a large, nearly perfect single crystal of INC, almost 3 centimeters long. It was phase pure with an almost perfect 1-to-1 ratio of indium to selenium, something nobody had ever managed before. The great mystery was finally about to be solved.
So, the moment of truth, when they finally tested this new, pristine crystal, they made an absolutely shocking discovery. Remember how the old indium-enriched samples were always N-type with all those excess electrons? Well, this new crystal was the complete opposite. Its true intrinsic nature is actually P-type. That means its charge is carried by holes, not electrons. The old recipe hadn't just been flawed, it had been hiding the material's true identity the entire time.
And the data here just seals the deal. This new crystal had over 10 times fewer of those unwanted, unintentional charge carriers than the old samples. This incredible level of purity finally lets scientists see the material's true colors.
Now, this discovery is so much more than just a cool academic victory, right? Creating this new, pure benchmark material, it literally opens up a whole new world of possibilities for technologies we haven't even dreamed of yet. And this quote really says it all. You see, getting to a pure, intrinsic material is the absolute foundation for any real innovation. It has to be the starting point. I mean, how can you possibly build a reliable device if your base material is a complete mystery?
So, what does this actually mean for the future? Well, take a look. Scientists now have a reliable, perfect platform to controllably dope the material how they want to. They can start building truly flexible electronics and thermoelectronic devices. They can study exotic 2D quantum effects. And finally, they can uncover the fundamental physics of this material that were hidden by all those messy impurities for decades.
So, you see, this breakthrough isn't an ending at all. It's the beginning of a brand new chapter. Solving this decades-old purity problem has given us a perfect blank canvas. And the only question that's left is, what incredible new technologies, from next-gen wearables to maybe even quantum computers, are we going to paint with it?